you can see my title for today, Dynamic Programming. Yeah. This topic. Yeah. It's the content of chapter 8. Yeah. Yeah. So this important topic, very late chapter 8. Yeah. Actually, this topic is an advanced topic. Yeah. It belongs to the level of graduate student level. Yeah. It's not an undergraduate student. Yeah. Graduate. Yeah. Yeah. But because in our module 3, when we study the Fibonacci numbers, we have a chance to use this method. So I will give you a simple introduction. Yeah. Very powerful idea, not very complicated. Very effective, yeah, very powerful. Yeah. Yeah, but I will not go very deep. Just a simple introduction. Okay? Yeah. Yeah. Because in the graduate study level, yeah, so students, they need to spend a lot of time, yeah, to explore this method. Yeah. Here, in this problem, Fibonacci numbers, it is very simple. Idea also very simple. Yeah. Actually, for the dynamic programming, this topic, the hardest part is deriving recurrence relation. That's the hard part. Yeah. The idea very simple. Yeah. But why it is so hard? Because most of the hard work is on developing recurrence relation. If you have a recurrence relation, then remaining part pretty straightforward. Yeah. Another reason, this weekend I will give you our second programming project. So this is one, the main method we will use in our second project. Just calculating dynamic programming using this method. And calculate Fibonacci numbers using this method. Then we do comparison. Okay? Brute force method, dynamic programming method, then we compare. How much is the difference? Okay? Yeah? So, give you impression. Yeah. Why this method is so important. Okay? Yeah? All right. Yeah. So the idea I mentioned the last time, but here let me summarize a little bit. Yeah. Why? In our current situation. So our current situation. Yeah. Last time I showed you, if we do not eliminate redundancy, eliminate redundancy, then the method we use straightforward recurrence relation. It's exponential. The efficiency is an exponential function. Yeah. Sometime later, I will show you why it is exponential function. Okay. Yeah. So later, after we, pretty much complete this module. Yeah. So I will show you why it is exponential. Yeah. All right. That's not acceptable. No. So in our computer algorithms, so later when you, go to your work, solving real world problems, yeah. So people have this understanding. Any exponential algorithm is not acceptable in computer algorithms. Okay? Too slow. No matter how powerful your computer is, still too slow. Okay? Yeah, not acceptable. Okay? Yeah. So That's our current situation. So we have to improve it. The good thing is the improvement could be this huge. From exponential function to linear function. How huge it is. Okay? Yeah. Linear function, yeah, people will be very happy. Okay? Yeah. So in most of the situations, if you can solve problems with efficiency as a linear function, yeah. So most of the time, people will be very happy. Yeah. Yeah. Yeah, but sometimes the efficiency could be, log, big of log. Remember our binary digits, counting binary digits? That problem is this one. Yeah. Better than linear function. Yeah. Binary search, yeah, in our module 4, we will learn binary search also in this category. Yeah. Other than those cases, yeah, most of the time, it is very hard to get a linear efficiency. Yeah. All right, here, summary, as a summary. So why we need to consider this dynamic programming. 2 reasons here. Yeah. The first reason, we want to keep the power of recurrence. Recursion, yeah, that's the recursion. Yeah. Okay, power. We know recursion is very powerful. Yeah, we don't want to throw away. Okay, yeah. Yeah. All right. So that's the reason. Yeah. Second reason, dynamic programming. Okay, yeah. Second reason. Remove redundancy. In computation. Yeah, these 2 reasons, 2 main reasons. So we need to use dynamic programming. Okay, all right. Next, let me explain. The idea is so simple. Yeah. All right. Method 2, dynamic programming. Okay. All right. Another name for it. Yeah. Some researchers, yeah, also called dictionary method. Yeah. Different people, yeah, especially at the beginning. Yeah. So different groups of people, they call this method differently. So some researchers call dictionary method. Yeah. The reason I give you this second name, because you can get an idea, dictionary. Yeah. The main method used here, you need to create a dictionary. Yeah. So you know what is a dictionary. Yeah. But here, what is a dictionary? We use dictionary to store our intermediate results. Okay? Yeah. Dictionary store, sorry, yeah. Mediate. Yeah, all right. Intermediate results. Okay. Dictionary, later we need to look up the data in the dictionary. Yeah. So there is a important feature of a dictionary. We can, any data item, we can look it up in the dictionary. Yeah. So that's why people use this name. Yeah. Yeah. If, because we need to check if the current data current value to be computed is available in a dictionary or not. If we calculate that value, then we should not calculate the second time, right? So avoid repeated calculation. The dictionary is used to help you keep track of your data. So you never need to calculate the same value twice. That's the usage of the dictionary, okay? Yeah. But you need to use extra cost because maintaining dictionary, you need some extra resource and computing cost. Yeah. Yeah. But that cost is not very, very high. Yeah. That cost, yeah. Just we increase our resource a little. Yeah. Because we know the storage is pretty cheap. Yeah. In current computing industry, the storage space relatively cheap. Yeah. So we're willing to, spend our resource to store the intermediate data. Yeah. But the saving is huge. We can save a lot of computation time. Yeah. All right. Yeah. Yeah. All right. So the main points of this method, we can still apply our normal recursive algorithm, yeah, but we can, in this, the modification part, yeah, dynamic programming, non-dynamic programming, if we do the comparison, the dynamic programming add this part. Yeah. So the main modification is here. Remove redundant calculation. Yeah. All right. All right. So that's the idea, right? So that's the main idea. Yeah. So this point is the, main idea. Is this. Okay? Yeah. All right. But how to make it happen, right? Yeah. Although we know it, everybody should agree this is a good idea. Yeah. So we want to remove all the redundancy as much as we can. Yeah. But the question is, how can you make it happen? Right? Yeah. That may not be easy. Yeah. How to make it happen? Yeah. Through smart arrangement of your data. Yeah. Organize your data. Yeah. So here, let's go back to the beginning of our first class. Yeah. In our first class, when we work on the chessboard question, yeah, we know a very important idea to solve that problem, we need to organize our data, right? Yeah. Into different categories. We know that step is important. Yeah. Here, we have a similar situation. We want to organize our data. Yeah. The purpose of organizing the data, because we can look up the data items in our data storage very fast. Very fast. Okay? Yeah? All right. So now, for the implementation data, then people will ask, how do you organize your data, right? Yeah. How do you find a very efficient way to organize your data? Okay? Yeah. Here, the idea. Use for this question. Yeah. Yeah. For the general question, yeah, so you need to extend this method. For this question, the way to organize, they are very simple. we just use an array. Okay? This array is used as this dictionary. Okay? What is a dictionary? Array is our dictionary. Okay? Array is, its role. We use this array. The role of this array is a dictionary. Okay? Because we can look up the items stored in this array. Okay? Use an array to store calculated values. That's simple, right? Yeah, so simple. Yeah. All right. Then make sure that no value is calculated more than once. Yeah. So that's the reason. Yeah. So this item explains, why we need to use this array. Okay? Because we want to make sure no value is calculated more than once. Yeah. So this sentence makes sure there is no redundancy in our calculation. Yeah? No redundancy in our calculation. Okay? All right. Yeah. Then, how to look up some number, some number to be calculated is available in the array. Yeah. How to look up? Yeah. Yeah. So here, another question. Yeah. So here, the detail of, so we expand this item. Yeah. Yeah. Now, let's assume you have stored all the intermediate values in your array. The next question. How fast can you look up an item in this array? How fast? Okay? You need to search, right? Yeah? Here, let me give you more specific information. Here, let's assume we are calculating Fibonacci numbers. And we store the intermediate Fibonacci numbers in an array. Yeah. Okay? Yeah. Next time, when we need to calculate a new Fibonacci number, given a new Fibonacci number, we need to do the calculation. But before we do the calculation, we need to check, is the value of this current Fibonacci number already available in the array? So that's what we need to do. Okay? Yeah. So now my question is, how fast can you do the checking? You need to do the checking, right? Yep. If the checking is so slow, then not worth it. So this method, not worth it. Yeah. So here, this question, how fast can you do the checking? Yeah. Yeah? Okay? Yeah. Rahit, idea? Some idea? Do the checking? Yeah. Yeah. All right. Fibonacci number. Yeah. Suppose currently we want to calculate Fibonacci number of 100. N equals 100. Okay? Yeah. But we store some previously calculated Fibonacci numbers. Right. But you don't know.
We need like 97 previously stored numbers for that, don't we?
Yeah. So we have an array. We store certain number of previously calculated Fibonacci, but 97 or 98, we don't know. All right?
I mean, it could get overwhelming depending on how large the number of stored values is.
Yeah. So here is our question. Is there a very fast way to do the checking? Right? Yeah. If the checking is so slow, not worth it. All right? So here, another question. Yeah. So here, let me draw a diagram here. Suppose this is our dictionary, all right? This is our dictionary. An array, okay? Yeah. Yeah. So we have consecutive locations to store our intermediate results, okay? Yeah. Index 0, yeah. 0, 1, 2, 3 consecutive locations. Okay, yeah, you mean certain number. Yeah. Yeah, let's say capital N. Okay, the last one. Okay, now, all right. So we store. Okay, yeah. Fibonacci 0 means we need to store f of 0, right? 1 f of 1, 2 f of 2. Okay, yeah. In that way. Okay, yeah. You know, the general location f of k, yeah, corresponds to index k. Okay, all right. Now, next round. Okay, yeah, because we need to do our recursion, iteration by iteration. Okay, yeah, yeah. Next round, current round. Okay, we need to calculate certain number. Yeah, let's say f of 100. Okay, yeah. Yeah, here I just use a simple example. Okay, f of 100. How fast can you check if the value of f100 is available in the array or not? How fast it is? That's the question. Okay, yeah. Is it very slow or very fast? We need to measure that. Okay, all right, all right. Another, yeah. So let me go another step forward. Yeah. We have learned as in module 2, not module 2, still module 1. Module 1, part C. Module 1, part C. We learned a topic, sequential search. Do you remember that? We do the search, sequential search. Do you feel here we need to do sequential search or not?
Binary search?
Yeah, binary search. Binary search requires sorting, right? So here, so
We don't know if it's sorted or not.
yeah, it is ordered. Yeah, Fibonacci number in the, it's ordered, right?
It's already sorted, so it's just binary search or weighted.
Yeah, good. Yes, good point. Binary search is much faster than linear search. Yeah, let's call linear search, right? Binary search is much faster. Yeah, although it's in our module 4 topic, but everybody knows binary search, right?
Search got a lot of time complexity to it.
Yeah, regarding the complexity, yeah. So I mentioned a little bit. Okay, linear search. Yeah, here I just write linear search, big O of n. Binary search, linear search, binary search, big O of. That's the difference. Huge. Okay? Yeah. Huge difference. Do you want to use the binary search here? Do you want to use the binary search here? Yeah. It is satisfied. Our current data satisfy the requirement for the binary search because Fibonacci numbers are ordered, right? Yeah, are ordered, ascending order. Yeah, yeah. So you can do the search. The question is, yeah, yeah. Is it a good way to do it? If it's good or not.
I mean, unless you think of anything more efficient, like hashing, for example.
Hashing, yeah, good. That's right.
So the first thing I was thinking of was hashing.
Yeah. Hashing, that's the topic of our module 5. Okay? Yeah. Yeah. He mentioned that hashing, search technique, hashing. Okay? All right. For the hashing, another search algorithm, but hashing, you need to build a hash table, right? Yeah. You need to build a hash table. All right? Yeah. So when you build a hash table, that cost is big O of n. To do the search is fast. After you build a hash table, then you do the search, big O of 1. Okay? After you complete building the hash table, then the search is extremely fast, big O of 1. That's the hashing. Yeah. All right? Yeah? Yeah. All right. Yeah, but here, you don't need those, you don't need to go that far. Okay? I mean, this search, try to look at all those possible search algorithms. You don't need to go that far. When you need to check f of 100, can you just go to the location 100 and do the check? Because you know where the location 100 is, right? Can you just go there and do the checking immediately? All right? How to do the checking? The next question is, you know where is F100. You know where is the location of that 100. But next, another question, how do you do the checking? How do you check if F100, its value is already calculated before? Okay? That's another question, right? Here you can see, we need to fix all the details. Then we can write our program. Yeah. After all these important details, all the points are addressed, then we are ready to write program. Okay? The last question. Yeah, this is the last question. After this question, then we can write program, dynamic programming. Okay? So this question, how do we do the checking? Yeah. We jump to that location, F100, F of 100. Okay? The checking. Yeah, so here, let me write the checking. Okay? We check this condition. If f of 100 is greater than 0. That's the checking. Okay? Yeah, because in this array, initial value, we need to initialize the array, right? Yeah, initial value. All the initial value, f of k equals 0. Yeah. At the beginning, the initial values for the whole array, any element, initial value of any element must be 0 at the beginning. 0 means its corresponding Fibonacci number is not calculated, right? It's unknown. In 0 initial value, let me say in this way. If f of k equals 0, that means the value of this Fibonacci number is not calculated, right? Yeah, 0, you never touch it. You never touch it, right? So it's a new Fibonacci value. That means you need to do the calculation. Yeah. After you calculate it, do you want to update this value? Yeah. After you complete calculation, okay? Yeah. F of k, I find its value. Do you want to update your dictionary? You have the value, right? You replace the 0 value by this new value. How about that? Okay? Update. So that means if f of k is greater than 0, that means this Fibonacci number has been calculated, right? Yeah, it's available. So that's why you only need to compare its value with 0. If it is greater than 0, then that means it's available, okay? Yeah. So this Fibonacci value available. Okay? It's available, right? Yeah. Checking is so simple. Is it faster than binary search?
That's what I was saying. Like it's a whole lot faster like that. You're just simplifying the criteria.
Yes.
For like determining if an operation is possible.
Yeah. So now everyone agrees it's faster than binary search, right? Yeah. Just do one checking, one comparison. How about that? Compare with the 0. You're done. Faster than binary search. Binary search, you need to do a lot of comparisons, right? Here, we only do one comparison.
There's got to be everyone who's still trying out with your search.
Yes. Yeah. So, all right. Then this method, can we say it's complexity or efficiency, the checking part or search part, whatever you call, we can say it's a big O of 1. How about that? The checking, look up in your dictionary, the lookup step, its efficiency is big O of 1. So good, right? Yeah, so good. Now we are ready to write a program. Okay? After we address all these important points in implementation. Yeah. So, yeah. We're talking about implementation, right? How to make it happen. Yeah. Yeah. Now, all the detail, all the necessary details we have addressed. Now we are ready to write the code. Yeah. Yeah. Here, let me give you the pseudocode. This is the pseudocode. Let me explain the pseudocode. Not too short, right? Yeah. Sorry, not too long. Yeah. Yeah. But a little longer than our, brute force implementation. Yeah. A little longer. But now we need to create an array as our dictionary. Okay? So what is the dictionary? This array. Known F, known capital F. Yeah. Known value. We want to use to check if the Fibonacci number is known or not. Yeah. So known F. All right. And its initial value. Here we skip the initialization. Yeah. There is an initialization step. Okay. Yeah. Because that step is trivial, right? So, yeah. So we do not specify it. After we create this array, by default, all the values are 0, right? Yeah, by default. So after you create a new array, the default values are 0. All right. Then, recursive function, fibo of parameter input I. Okay, all right. I, yeah. Temporary storage variable S. S is used to store the, intermediate result, calculation result. Yeah. All right, so let me erase this a little. Yeah. All right. So then, first time we need to check Fibonacci number of I is available or not. This is the checking step, right? If known F, this is the dictionary lookup. Yeah. Known F of I, this is the value we find in the dictionary. That's the value. Okay. To get its value, straightforward. We get to the location immediately. Yeah. So this already the lookup step. Okay? This is already the lookup step. Known F of I greater than 0 if it's true, because it is already calculated. Don't do the calculation, so you return the value directly. No calculation, just return it. Simple, so simple. So you do not need to do the redundant calculation. This return, okay? So avoid redundancy, right? This return line, so simple. No redundancy, right? All right. Yeah. If not true, if this condition not true, that means the Fibonacci number for index I, for input number I, has not been calculated before. You need to do the calculation. Okay? Now you need to do the first time calculation. Yeah. First time, you cannot skip. You have to do the work. Okay? Yeah. Now, we do the work. Yeah. 2 base cases. Yeah. That's simple. 2 base cases. After the 2 base cases, now we consider the general case. The general case, all right, recursion. You can keep your recursion. So this is a recursive function call. Yeah. Yeah. You keep your recurrence relation. Yeah. Yeah. So you can enjoy the power of the recursion. Okay? Yeah. The power. Yeah. All right. Yeah. And here we don't worry about the redundancy. Do you all worry about the redundancy in the first one, second one? Right? Do you still worry about the redundancy here, redundancy? No. You never need to worry about the redundancy. Because when you need to get a value 5, then because this line always guarantees the value of this Fibonacci number is only calculated once. No. Don't worry. Yeah. Yeah, because that line guarantees no repeated calculation. Also, no repeated calculation. You just treat these 2 numbers available, add them up. Okay? Yeah, because the dictionary will help us retrieve the values of those 2 numbers. Yeah, the dictionary will take care of that part. Okay? Yeah? Simple, right? Yeah. So then you store in this temporary variable s. Yeah. All right. Then the last step, before you return, yeah. So although you can return s, but before you return, you need to update your dictionary. Okay? Because known f of I should not be 0 anymore, right? Yeah, because after you pass the line, yeah, at this point, known f. Yeah. So at this point, yeah, let me look. Because after you pass the line, you are here. Yeah. At this point, the value of known f I equals 0. Okay? Yeah. Yeah. So we're here. Yeah. But after the calculation, this is the first time you calculate this value, right? The first time. Yeah. After the first time calculation, you should update your dictionary. Okay? It is not 0 anymore, right? Otherwise, if you do not do the updating, next time you need to calculate another time, right? That's the repeated calculation. You don't like it. Okay? So this update step, make sure you only do the calculation once. Yeah. Just simple update step, right? Simple assignment. Assignment we know is very fast. Yeah. Assignment operation, very fast. So our data updating, very fast. Yeah. So let's update it. Yeah. Then the whole thing works well. Okay? No redundancy. Still, recursive algorithm, yeah, with a small modification. The modification part, you add a dictionary. Okay? You add a, storage data structure here. Our array, that's our storage data structure to store the intermediate data. Yeah. Intermediate results. Yeah. Intermediate results. Yeah. Yeah. Pretty good, right? Yeah. Idea is so simple, yeah, but very effective, very powerful, very useful. Yeah. So that's the reason. Yeah. So I want to bring it here, chapter 8 topic that I want to bring it here. Because when we learn Fibonacci numbers, it's a perfect place we study this topic. Right? Yeah? Yeah. All right? Yeah. So in your programming project number 2, you can practice a little bit. Yeah. Writing the code here, the pseudocode given, writing, so simple, right? So easy. Yeah. So project 2 also very easy. Very easy. Not too much work. Okay? Yeah. If I assign you this weekend, you have more than 1 month to complete it, right? Yeah. Although the completion, the deadline close to final. Yeah. At that time you will be very busy. Yeah. Close to final. Yeah. But writing the code is so simple. Okay? Just to let you feel about it. When you do the experiments, you need to do experiments. Yeah. Yeah. Think about the idea of dynamic programming. Okay? To have a good understanding. Yeah. Yeah. And if you understand this method well, yeah, so in your real world situation, you have pretty good chance to use it, right? Yeah. All right. Yeah. So, yeah. Let me complete this topic. I spent a lot of time here. Yeah. Yeah. All right. Next, then we need to go to the mathematical formula development. That step. Yeah. So here, although in our second part we need to apply a lot of math, yeah, but there are many problem-solving methodology issues we can learn. Okay, yeah. Also, useful. So we need to learn a lot of strategies, techniques in problem solving here. Yeah, this part. Okay, yeah. All right. Topic 3.2, golden ratio. First, so you may have heard of this golden ratio. So here, let me describe a little bit. So what is a golden ratio? Okay, all right. Yeah. First, this golden ratio number closely related to the Fibonacci numbers. Yeah. So that's the reason we talk about golden ratio here. Closely related to the Fibonacci numbers. Yeah. All right? Yeah. How? Yeah. First, we know the Fibonacci numbers, when we start 0, 1, then the sum of these two numbers also 1, then 2, then 3, then 5, 8, 13, and so on. All right? Yeah, like that. First few. Okay? Then, here, some people discover a way to arrange these numbers. Okay? Each Fibonacci number using a square with that Fibonacci number as its side, the length of the side. Okay? Yeah. Yeah. Square with the side, yeah, 0 we skip, because 0 nothing, right? So we cannot draw a square with side 0. Okay? Yeah. So we skip the 0 one. All right. Then the first square, side 1 square. Okay? Second square, also side 1 square. Okay? So we arrange. Yeah. So we, align their sides. Okay? So you get a rectangle. Yeah. Then the next one, side 2, then we can, align them in this way. Yeah. So you get another rectangle. Then we can extend the rectangle. Side 3 square, side 5. So every time when we add one more square with the side as the next Fibonacci number, yeah, you always get a nice rectangle shape. Okay? Yeah. All right. Then after that, then we draw a quarter arc in a special way. No. All right, so here, each square, we can draw a quarter arc, okay? With the center here, yeah, quarter section, right? Quarter section, the arc, all right? Yeah, all right. So here, sorry. The first one, okay? This quarter arc, quarter arc, quarter arc, quarter arc, quarter arc, quarter arc, okay? See? Yeah. Keep doing like this. Yeah. When we extend the rectangle, we extend the, the curve, joining all these quarter arcs, so we get a nice spiral curve, right? Nice spiral curve. Yeah. Looks pretty good. Yeah. So here, something like people just want to explore the nice properties related to the golden ratio and also related to the Fibonacci numbers. Golden ratio and the Fibonacci numbers. Yeah. Here. All right. So here, some people also argue, so in a, famous painting, yeah, try to measure the location, some, key points, yeah, corresponds to these Fibonacci numbers and the golden ratio, okay? All right, so then I need to talk about the definition. So what's the definition of golden ratio? All right, golden ratio in ancient time, okay? Yeah, ancient time, Greek, ancient time. Yeah. Right. Ancient time. Yeah. The first time. So we know people at that time, the ancient time, people want to understand the world, right? Understand the natural world. Okay. So when they understand, based on their understanding, they make some stories. Okay? Yeah? Imagine, using imagination to make nice stories as the understanding way of the real world. Okay? There are many different ways to understand the real world, right? Yeah. So, yeah. Then, some people think about, so what number is the most natural, most beautiful, special, natural number in the real world? People try to think about that. Okay, you need to make a story to justify your argument, right? Yeah. Then some people they make the story like this to justify one special number is very special and very natural to get that number. Okay? Yeah. So use line segment. Yeah. One longer line segment, one shorter line segment. Yeah. When they make the story, they want to make the story not very trivial. If your story is so trivial, then not interesting, right? So the story should contain some technical difficulty. Otherwise, you say, number 1 is the most beautiful number in the world. Yeah. Probably, so that's, yeah. Right. Yes. Yeah. So here, just some people try to create some very special, non-trivial example to justify. So this number is very special. Okay? Yeah. So it's a non-trivial number. Okay? It's not easy to get this number. First, it's not easy to get this number. But second, there is a beautiful story behind it. Yeah, that's the point. All right. Now, so people make that beautiful story. Given a line segment, the first one, we use little a to represent its length. Yeah. Then another line segment shorter. Yeah. So one longer, one shorter. The longer one, we use A to represent its length. The shorter one, we use B to represent its length. Yeah. And here, so those people, they don't want these two line segments have the equal length. Yeah. Otherwise, the ratio is not interesting, right? The ratio of two line segments with equal length equals 1. That's trivial. Yeah. So they want to make some non-trivial number. Yeah. All right. Then consider the ratio of these two line segments, A over B, the longer one over the shorter one. So we know the ratio must be greater than 1, right? Yeah. All right. Then, in order to set up equation, yeah, another ratio is needed. Now, another ratio with value greater 1 should be used to compare with the first ratio. Now, how to get a second ratio of line segments with value greater than 1? Yeah, here, another option. A plus B, we know, is longer than A, right? Greater than A. So we use A plus B over A to have our second ratio greater than 1. Then make these two ratios equal. Then that's something special, right? Yeah. So this equation, this time, yeah, because when this equality holds, some special could happen, right? Yeah, yeah. Because in general, this equality does not hold. Yeah. Only under the special condition it holds. Yeah. Here we want to find that condition. Yeah. All right. Before we try to find the answer, we need to change the form of the right-hand side of this equality. Yeah. Let's simplify the fraction representation at the right-hand side. Yeah. 1 plus a b over a. Yeah. So we split the fraction two parts. The first part, a over a, that's 1. Then the second part, b over a. Yeah. All right. Now you see, for this equation, in order to solve it, first, let's observe the properties of this equation. There are two unknowns, A and B, two unknown variables, but we only have one equation. Based on our knowledge on the equations, we know in order to solve equations with two variables, we need at least two equations, right? We need two equations. Yeah. One equation is not enough for us to solve the equation with two variables. Yeah. So for that reason, yeah, we should do something different. Yeah. All right. Here, actually, if we look at the original question, we notice that the specific length for A and also specific length for B, not very important. The most important thing we want to know, that is the ratio of these two line segments. Ratio is more important. The specific length, longer, shorter, we can stretch, right? Longer, shorter, we can scale up and down. So the concrete lengths, not important. Okay, yeah. So for that understanding, we can introduce a new variable to represent the ratio of A over B. Yeah. So here, let's use x to represent our destination quantity, A over B. Yeah, that's x. Yeah, one variable. Here you can see one variable, we use it to represent a representation involving two variables. Yeah, that's no problem. Then the second part, after this variable substitution, we also need to represent the right-hand side. How to represent B over A? B over A. Yeah. All right. So here there is an easy way to represent B over A ratio. That is reciprocal of x. Reciprocal of x. 1 over x. Okay? Yeah. Can you see it? Yeah. Yeah. So in class, one student asked me, how do you see it? Yeah. All right. Here, let me explain how to see this. Why we use 1 over x, we can represent B over A. Yeah. Yeah, there are two ways to see it. The first way, straightforward way. The first way, the B over A ratio, can you see it is 1 over A over B? Direct, straightforward way. Yeah, because when you take a reciprocal of a fraction, you flip numerator and denominator, right? Upside down. When you make the flip, you get it, right? So because here the denominator A over B, that's our variable x. So it becomes 1 over x. This is the first way to see why B over A equals 1 over x. Then we have second way to see it. Second way, this time, because we want to see the relationship between these two fractions. The first one is A over B. The second one is B over A, right? The relationship. Then let's multiply these two fractions together. After you do cancellation, equals 1, right? Yeah. So we start with the simple identity. Now, then, by our variable substitution, the first fraction should be x, right? Yeah. The second fraction, yeah, temporarily, if it is unknown, we put a question mark here. X times something equals 1, right? Yeah. And how do you see that question mark? Right? Yeah. Yeah. So by the simple algebraic operation, you can see that simple, that question mark equals 1 over x. Yeah. So that's the second way you'll see why we can use B over A in terms of x, right? Yeah, 1 over x. All right. So after that, now we simplify our original equation to this new equation. This new equation is a one variable equation. X equals 1 plus 1 over x. This equation. It's much simpler. Now, in this new equation, we have only one unknown variable, one equation with the one unknown variable. It is solvable, right? Yeah. So now we have the confidence to solve it. Yeah. All right, so next, let's solve this equation. Yeah. To solve it, the first step, we need to do the transformation to make this equation more friendly for writing out the solution, right? Yeah. So let's remove the common denominator. So we have this nice form. X squared equals x plus 1. Yeah. So this is a quadratic equation. And we know there is a quadratic formula to solve a quadratic equation. Yeah. So let's apply that formula to solve it. All right. Here, our current quadratic equation, before we can apply the quadratic formula, let us write it in a standard form. Yeah. Yeah. All right. the quadratic formula is applied on the standard form of the quadratic. So this is the standard form. Okay. So we move all the terms to the left-hand side. Yeah. Yeah. So with coefficients A, B, C, in order to get a valid quadratic equation, we need to assume the leading coefficient A cannot be 0. Otherwise, it's not a quadratic equation. Yeah, it becomes a linear equation, right? Yeah. So under this condition, so we can write out, this is the quadratic formula. Okay, yeah. Well-known formula. Yeah. So now let us plug in A, B, C, 3 coefficients for our current quadratic equation. Yeah. So this is the standard form of our current quadratic equation. A equals 1, B equals -1, C also -1. Now let us plug in into the quadratic formula. Okay, yeah. So now this is our solution form. There are 2 solutions. One plus minus. Yeah, here plus minus. Plus is for the first solution, minus for the second solution. So plus minus √5, then the whole thing divided by 2. Yeah. So 2 possible solutions. Yeah. But we need to, after we derive the 2 solutions, we also need to go back to our original question to do the interpretation. All right. So first, we need to go back to see what is the meaning of x. What is the meaning of x, right? Yeah. Based on our definition, x equals the ratio of A over B. Yeah. Ratio of the lengths of 2 line segments, A over B. And it's easy to see this ratio must be a positive number, right? Yeah. Yeah. Because both A and B are positive. So their ratio must be positive. Yeah. But if you look at the expression here, the first solution, 1 plus √5, it's positive, no problem. But the second one, when you use the minus sign, 1 minus √5, it is negative. Then your second solution is a negative solution. Then it does not make sense. Because its original meaning, the ratio must be positive. Now you give me a negative solution. So you cannot go back to the original story, right? Yeah. It does not match, not compatible. Yeah. That means we should draw the second solution. We only keep the first solution. Okay, all right. So our next step, let us drop the negative solution. So we only have one solution. X equals 1 plus √5, then over 2. Yeah. And this number, yeah, this number, first we see it's non-trivial, right? Yeah. Yeah. Because in the general situation, it's not easy for people to come up with this strange number, right? A little strange, yeah. But here, people like to see the special form of this number, constant, yeah. All right, its approximate value is 1.618, approximate value, yeah. Yeah, but this is the exact value. So that is the approximate value. Yeah. Yeah. So then people call this number golden ratio. golden ratio. Yeah. Golden means it is very important. It is very interesting. It is very useful. Things like that. So the golden ratio. Yeah. But although there is some nice story behind it, but when people really need to use this number in the real world applications, it is not convenient to always copy this relatively complicated form, right? So then, for convenience, people use a special symbol, Greek alphabet, phi, to represent this special number. We have similar experience before. Remember, we use another Greek alphabet pi to represent, some well-known constant. Pi here, phi, not as famous as that pi, but still some important constant. All right. So with that, then later from now on, so we need to use this, important constant in our calculation. All right. So the next, we need to get to the Fibonacci number formula. But let me leave the remaining part of the story to our next lecture. All right. So let me stop right